Yeah.
All right, so one of the questions was about change of state. And so I'll use this side for my notes over here. So we start out with BTU, British thermal unit, the amount of heat required to change 1 pound of water, 1 degree Fahrenheit. Sound familiar?
Yep.
Right, so if I have water, and water is at 32 degrees Fahrenheit, all liquid, and I want to change, and I have 1 pound of that, and I want to change that from 32 degrees liquid all the way to 212 degrees Fahrenheit liquid. Still keep it in liquid form. How many BTUs for 1 pound?
One.
From 212 to 32?
180.
Let's make a little formula here. So if it's going to be sensible heat, it's going to be blank pounds of water times our temperature change. And simplicity times 1 equals blank BTUs. So how many pounds of water are we using? 1 pound of water. So I'm going to put pounds of water. I'm going to put 1. And now our temperature change. What was our temperature change?
180.
So we got 212 minus 32. So 212 minus 32 equals 180 degrees temperature change. So here I'm going to put temperature change, 180. So what's 180 times 1? Good! Your math's improving. Now 180 times 1 is 180. Now times 1 is 180. So it's going to take us 180 BTUs to go from 32 Fahrenheit liquid to 32 Fahrenheit liquid.
To 212.
Sorry, to 212, yes. Put it like this. 212 degrees Fahrenheit. And this would be, can I measure this temperature change?
Yes.
So this would be sensible, right? Sensible heat, and in this case, it was 180 BTUs to make that happen.
So if there's 2 pounds, it's 360 BTUs.
Yes, exactly. I would just change my number of my pounds there, and all those numbers change. So let's take that 1 pound of water from 212 degrees Fahrenheit liquid and change that into 212 degrees Fahrenheit vapor.
970.
The 1150 total? The 970 changes to be.
970 BTUs. Is that sensible or latent?
Latent.
It is latent. Latent. So for that one, we could have, let's see here, blank pounds times, and we're not going to have any temperature change at all, right? So it's going to be times 970, that's a given, equals blank BTU. So how many pounds of water we're changing? 1. So what's 1 times 970? 970. Right? So is that going to be sensible or latent? That's going to be latent. So over here, I'll just move this over a little bit. Over here, I'm going to put sensible. Over here, I'm going to put latent. Okay. So the other thing that we learned before was taking 32 degrees Fahrenheit solid. To 32 degrees Fahrenheit liquid.
144.
And it takes 144 BTUs per pound. And is that sensible or latent?
So
Specific, something different. We're not getting into that yet. So we have blank pounds times a simple 144 equals blank BTUs, and that's latent. So we had how many pounds? 1. So 1 times 144 equals? 144. Good, so that's what we've already learned. Now there's something else we didn't talk about, and that is the specific heat content of ice changes after it becomes a solid. Can I have ice at 32 degrees? Can I have ice below 32 degrees?
Yes.
Absolutely right. Yes, we can. So, can I have ice at 20 degrees?
Yes.
Good. So if I had ice at 20 degrees Fahrenheit, what state is it in? Solid. It's a solid answer.
6 BTU.
So let's hold on a minute. So first off, let's take and find out what our temperature difference is. So we have 32 minus 20 equals 12 degrees Fahrenheit. 12 degrees temperature change. So we're going to have blank pounds times our blank temperature change. So what was our temperature change? 12. How many pounds? 1. So 1 times 12 equals? 12. Good. Except now we have another factor here.
Times 0.5.
BTU was 1 for liquid. But BTU to change 1 pound of solid ice, 1 degrees Fahrenheit, takes 0.5 BTU. So what's 12 times 0.5?
6.
So our answer here is going to be sensible heat, because we can measure it. But it's going to be 6 BTUs. So right here, this will be sensible. We can measure it. It's going to be 6 BTUs.
So the 0.5 was the amount of BTU required to change solid to...
Not to change solid, to keep it solid, but to change 1 pound of solid ice, 1 degree Fahrenheit, is 0.5 BTUs. And we also have the vapor side of it. What number was it? 220, I think it heated it up to? So if I'm at vapor 212, can I change the temperature of vapor?
Yeah.
So let's change it to 220. It's still going to be vapor, right? So there's a change of temperature without a change in state. That's going to be sensible. Okay, so it's sensible heat. So what's 220 minus 212? 8. So it's 8 degrees temperature change. So still a little formula here. We have blank pounds of vapor times blank temperature change times, and again, because we have a density change, specific heat change is going to change to 0.5 equals blank BTUs of sensible. So we have how many pounds? 1 pound. Our temperature change was 8. So 8 times 1 equals 8 times 0.5 equals 4. So it takes 4 BTUs of sensible heat to change water vapor from 212 to 220. Because it only takes half a BTU to change water vapor 1 degree Fahrenheit. Because we have a density change. So, temperature change, 212 minus 32, 180. No temperature change, 220 minus 212 equals 8. So here, if we calculate this being BTUs across here, this being temperature change up here, we have several states going on. We have to take it from solid to solid temperature change. So if I'm going to put heat into it to make the temperature of ice go up. So I apply heat to it. I put into this 6 BTUs of heat. So if I put 6 BTUs into solid ice, 1 pound, it's going to take it from 20 to 32. And here's our formula. 1 times 8 times 0.5 is 4 BTUs. Now, this one. 1 pound times temperature change of 12 times 0.5 is 6 BTUs. So take 6 BTUs to go from 20 solid to 32 solid. But now I have to melt that ice. This is the magic of latent heat. So it takes 144 to melt it. So I got to put 144 BTUs in there. So 1 pound of ice times 144 is 144 BTUs. There's 144 BTUs. Put a little note here, BTU. But now I want to take that it's now 32 degree liquid, so I take it from 32 liquid to 212 liquid. I have to put in that 180 BTUs, sensible heat. So here we got for heat, 1 pound times 180 temperature change times 1 is 180. So 180 BTUs there. Now I got to change state again from 212 liquid to 212 vapor, 970 BTUs per pound. 970 times 1 pound is 970, so it's 970 BTUs. Now that it's all vapor, I can still change the temperature. So we're going to take it from 212 vapor to 220 vapor. It's all measurable, all sensible. So it's 4 BTUs. So total, how many BTUs would it take to change, to raise the temperature 20 degrees solid to 220 degrees vapor? It's going to take 6 plus 144 plus 180 plus 970 plus 4.
1304.
1304. So it take a total of 1304 BTUs of heat energy to make that happen. Or if I had water vapor at 220 degrees and I wanted to freeze that, not only freeze it but drop that down to 20 degrees, I'd have to remove 1,304 BTUs of heat energy. So if I want to go this way, I have to add heat into that. If I want to go this way, I have to remove heat out of that.
No, I have a question.
Sure.
Okay, it makes sense why it would only take, times 0.5 for the water vapor because it's not as dense.
Yes.
But ice is denser. So
No, ice is less dense.
Then it is?
Well, it's well, I see what you're saying, but it's less dense than liquid. Ice is one of the very few things. Water is a very unique thing. But because, think about if I dropped ice on the water, where's ice going to go?
Floats.
It's going to float. So ice is less dense than water. It actually spreads out as it freezes. Most things, when you freeze it, it gets closer together. But ice is unique. When it freezes, it becomes less dense, so it floats on top of water. And vapor also floats on top of water. So they're both less dense than water.
Okay.
So it changes their specific gravity. It changes their, not specific gravity, but specific heat content. So it's going to be different.
The density of ice is the same as vapor?
I wouldn't think so, but yeah, according to
Then that would make sense.
yeah. I don't know
Far out.
all the details about in detail and density, but yeah. And also, so everything will have a specific heat content. The specific heat content for water is 1 BTU to change 1 pound of water 1 degrees Fahrenheit. But everything can have a specific heat content. So this metal can have a specific heat content. It takes so many BTUs of heat energy to raise 1 pound of this steel 1 degrees Fahrenheit. This plastic can have a BTU content. It takes so many BTUs to change 1 pound of this plastic 1 degrees Fahrenheit. Air has a specific heat content. It takes so many BTUs of heat energy to change 1 pound of air 1 degree Fahrenheit. So everything has, if you want to add sushi has a BTU content. It takes so many BTUs to change 1 pound of sushi 1 degree Fahrenheit. So when we're cooling stuff, freezing stuff, etc., we know how many BTUs it takes to change that. And if I want to make it change states, engineers actually calculate all this, what we need to make happen. For example, let's see where to put it. Here we go. I got this little device here. You guys know what this is? Yeah, steamer. So what do we put in here? Water. Water has weight, right? So we put water in, room temperature water, and I plug this in, and it has to sensibly heat the water from whatever temperature it is all the way to 212. Then what it has to do to make steam is change that from liquid to vapor, which takes heat energy, right? So they have to calculate how much heat energy it's going to take from a typical room temperature water to 212, and make it go from 212 liquid to 212 vapor. That 212 vapor is what we need to put the moisture in the clothes to take the wrinkles out. So they need to know how many BTUs of heat energy they need to put into this. And they don't need to do that in an hour. They need to do that in so many minutes. So they have to then divide that into minutes to make that happen. So then they know how many BTUs. Well, now they know what size heater they need to put in here. Well, they got to make sure that heater is the correct size for the wires. So what are we buying to put into this? Electricity. How do we buy electricity? In watts?
Kilowatt.
Can we convert BTUs into watts? It takes, for every 1 watt of energy, it's 3.413 BTUs of heat energy. So they calculate, if you look in the bottom, it says here 850 watts. So it has 850 watts per hour. 850 times 3.413. What does that come out to? 850 times 3.413?
Let's see.
2901.05.
29.0.
No, 2901.
2901 point, oh, it's 2901. 2,901 BTUs. So this has a BTU rating of 2,901 BTUs per hour. So in other words, we can change 1 pound of water to a vapor every hour, 1 full pound. And we got to drop it down into minutes, and it's all calculable. They do this. It's not that we're going to be doing all this in the field. They want to make sure that we have an appreciation for change of state. Are we going to be making ice?
Yep.
Yes, ice machines, right? Ice machines have a rating of so many pounds per hour. So we're going to take ice, and we're going to change it from 32 liquid to 32 solid. Ice, they actually like to keep ice at 32 degrees. Because if we make ice below 32 degrees, it takes a lot of energy to make that temperature-wise. We're gaining a lot of temperature from the air, but it doesn't really have a big BTU content. It doesn't help us make things
Cool.
It's that ice melting is what the magic is. So we're going to take ice from liquid to solid, but we don't really need to worry about going too much farther that way. And we like to keep our water cool. As that water is circulating, we like to keep that water about 32, not yet freezing. And as we run that over the ice, or over the evaporator coil, we absorb the heat out of the ice. We're going to make ice change state. And in the air, is there moisture in the air? Not much, so much here, but let's think about Florida. I asked before, but some of you guys been to Florida? What was it like in Florida? It's humid. The temperature could be the same, but it's going to feel much warmer in Florida. It's going to feel, the air is going to feel sticky, but it's not the air feeling sticky. It's your own sweat not evaporating that feels sticky. So how do we make it feel cooler at the same temperature? Dehumidify. Pull the moisture out of the air. So when we pull water out of the air, can we measure how much water we're taking out of the air? Yes, we can measure it in gallons or really pounds, right? So for every pound of water I want to pull out of the air, that's 970 BTUs of heat energy that my air conditioner has to have of capacity. And I got to reject that outside in the condenser. So I got to pull the heat in the evaporator, inject it into the condenser outside. So in Florida, it's very easy to pull out 5 gallons of water in a day. You can fill out a 5-gallon bucket in one day from your air conditioner.
So that's why if you open the door, people yell at you.
Yes.
Humidity back in.
That's right. Let's say 5 gallons. You guys remember how much 1 gallon weighs?
8.123 something.
8.3 something. We'll just put 8.3. So what's 5 times 8.3?
41.5.
41.5? Okay. 41.5. Okay, so 41.5 times 970.
Pull up the machine for that one.
A little bit less than 3 zeros, that's good.
So you guys have calculators. I'm not making you do with manual math. I'm not making you learn the formulas here.
255.
40,000.
255.
So it takes 40,255 BTUs of capacity of my air conditioner, because I got to take that moisture out of the air. That means I got to take heat out of the moisture, right, to make it change state.
Yep.
And it's not going to happen necessarily at 212, but I can make it change state. So I got to remove from water, from 5 gallons of water, I have to remove from that water 40,255 BTUs of heat energy. Our air conditioners are sized in tons, which also goes down to BTU, 12,000 BTUs per hour. So it means of my air conditioner's capacity, I got to use some of that capacity to just dehumidify. So it's going to take energy to take the moisture out of the air. Not just cool the air, but it takes energy to take the moisture out of the air. And I lose some of my capacity. My air conditioner has a capacity of, say, 36,000 BTUs per hour. and I got to divide this down. This is per day, so I got to divide this down how many gallons per hour, how many pounds of water per hour. You calculate exactly how many BTUs.
Air conditioner here is gonna be much more efficient than the exact same air conditioner in Florida.
Not necessarily efficient, but you have a different difference of what it's moving. Here, you're changing mainly sensible heat of the air. So a lot of the air conditioners here just very seldom have any moisture coming out of it because your humidity here is so low already. But in Florida, the humidity is much, much higher. So you need to dehumidify. So in Florida, there's water coming out of that drain constantly all the time. Here, sometimes people never even see water coming out of their air conditioner until that one day that it rains and the humidity goes up and your AC starts to dehumidify and they're like, oh, why is there water coming out? But it's because of the latent heat capacity of it. Going beyond, the density changes, so it changes it. So more than anything, we're trying to get you to see that it takes energy. That latent heat can work with us or against us. We want the refrigerant changing state from a liquid to vapor, absorbing massive amounts of heat. But as far as the air goes, the air going from a vapor to a liquid, it gives up massive amounts of latent heat, right? So it's not that we're going to be calculating this often, but they just want you to see the difference between sensible, latent, sensible, change of states, how it's happening. The more that you see that, the more you get into it. So if you got that wrong, it's okay. I'm not worried about that, but I do want you guys doing it. And the more that you do it, the more you see it.
When you do the calculation for the 40,000 BTU to extract the moisture, why is 970? Because the saturation temperature should be 212, but the air temperature shouldn't reach 212 degrees.
Right. No, there's other aspects because we don't have just water and water vapor in the air, do we? We also have nitrogen and oxygen and dust and everything else in the air. Okay. So because we have all these other things going on in the air, there are other numbers involved in that. So we can make water has what we call a dew point, the point that it changes from a vapor back into a liquid, and it depends on how much moisture is in the air. But we calculate this, and we'll be doing this later. We got to get with the psychometric chart and stuff like that first. But yes, we can calculate it, and it's because it's not a pure blend. Here we have air. We're going to have a difference between, if this is a pure refrigerant, if it was pure water and water vapor, then yes. But because we have other things going on, then it's different.
Okay.
Yeah. It's a little bit more complicated. It's a good question. What other questions you have? No? Good? Okay, good.